In this video, we are discussing how to analyze LTI system, that is linear time invariant system, using Fourier transform. Already we know to find out the output response of LTI system, we are using convolution integral. So in this convolution integral, y of t, that is the output response of a continuous LTI system, is equal to input x of t is the input response convolved with the h of t, that is the impulse response of a system. So here, as it's a continuous signal, so we are using convolution integral. So applying convolution property, cumulative property, we can say h of tau multiplied by x of t minus tau d tau. Okay. Now in this example, we are considering input response as equal to exponential signal e raised to j 2 pi ft. So here we replace x of t minus tau with the e raised to j 2 pi, t replaced with t minus tau. So after solving this integration, we are getting y of t is equal to e raised to j 2 pi ft h of into h of f. So by this we can in the position to find out h of f, which is in frequency domain. So h of f is equal to h of t into e raised to minus j 2 pi ft dt. This is the Fourier transform formula. So with the help of this, we are in position to find out the transfer function. Now what do you mean by transfer function? So see here, the transfer function is equal to h of f is now the system transfer function, which is equal to output upon input. So that's why here y of f is the output response in frequency domain divided by x of f input response into frequency domain. So we can find out even the output response in time domain. For that purpose, we have to find out the Fourier transform of system response. Using applying the Fourier transform formula, we can find out h of f, okay, and find out the Fourier transform of input response, that is x of f. And already we seen the Fourier transform property that if we are doing convolution in time domain, see here, the if we are doing convolution in time domain and if we apply the Fourier transform, then there is a multiplication in frequency domain, which is easy comparatively convolution. So what we can do, convert the given impulse system response and input response by applying the Fourier transform formula into frequency domain and take simply the multiplication, by which we are in position to get output response in frequency domain, that is y of f. And by taking the inverse Fourier transform of y of f, we are in position to get the output response in time domain. And with the help of this same also, we can analyze the system response, that is h of f is equal to y of f divided by x of f. For the same, which property we are using, this property is very important, that convolution property of Fourier transform. If we are doing convolution in time domain, we can perform multiplication in frequency domain. Okay, so with the help of this, we'll try to see some numerics with the help of this interconnection system. So already we discussed the interconnection of a system in our unit number 2, that if the two LTI systems, see in this figure 3.42 figure, if the two systems are in cascade connection, that is in series connection, that is the two LTI system H1T and H2T are in series. So by applying cascade connection, what we are performing here, to find out the output response y of t, our system interconnection is make a convolution in between H1 convolved with H2, correct? So in place of this two system box, we are getting one system box that gets convolved with our input response. Okay, now here how we have to solve two convolution. In place of that, we convert this time domain into frequency domain. So and we can apply here the Fourier transform. So what we can do here, convert h1 of t, h2 of t and x of t into frequency domain with the help of Fourier transform, by which we are getting h2 of f, h1 of f and x1 of f. And here Now we are applying convolution property. In place of doing convolution in time domain, we can perform multiplication in frequency domain. So in place of this convolution, simply here we are performing the multiplication. H2f multiplied with H1f multiplied with X1f. Correct. So with the help of this, we can say here H2f multiplied by H1f is nothing but H of f. Okay. In the same way, for the parallel connection, already we know if there are the two systems are in parallel, we perform the addition. Okay. So after solving this bracket, what we are getting, x of t convolved with h1 of t plus h2 convolved with xt of t, by which again here we can apply the convolution property, and in place of convolution in frequency domain, we are doing here multiplication. Okay. So see, now this numerics are very easy, because already now we know how to convert the given signal into frequency domain and how to apply the convolution property in the frequency domain. See this numeric, I'll read the numeric. A signal x of t is equal to 10 direct t is applied to the input of the LTI system as shown in figure, and LTI system frequency response is given h of f. So see here, dear students, for this LTI system, x of t is given to us, that is the 10 direct of t. H of f is itself is given in frequency domain, and what we have to find out here, y of t, that is the output response. So what we can do, we can convert this given x of t into frequency domain, and already we see that the rectangular Fourier transform is sinc. So simply we convert this x of t into frequency domain. So what we'll get, a tau sinc of f tau. So here we can say 10 sinc of f. Now input is also in frequency domain, system response is itself is given in frequency domain. So what we can do to find out the y of f, use the convolution property. In place of doing convolution, as this both x of f and h of f both are in frequency domain, we can perform here multiplication. So what is the y of f? 10 direct means multiplication of x of f into h of f. So it is very easy comparatively convolution in time domain, and this is the frequency spectrum plot shown to us. Okay, so this is the input response in frequency domain, sinc pulse. This is the system response, that is rectangular, and if we taken the multiplication, so rectangular signal is present up to only -1 to +1. So multiplication of these two signals is nothing but only -1 to, this is the our output response. Okay, so we will see one more numeric. The determine the frequency response of system which is described by its impulse response. So here impulse response, that is h of t, is given which is equal to delta t minus 2 e raised to minus 2 t u of t. So what is the question? Sketch the frequency response and comment whether the system is low pass, high pass or band pass. So what we can do, we can convert this given h of t into Fourier transform. Already we know delta t Fourier transform is equal to 1. 2 into e raised to minus 2t u of t. So e raised to minus a t Fourier transform is 1 upon a plus j 2 pi 2f. We applied it here. Okay, take a LCM, and what we are getting, this is the h of f. So if we try to plot this h of f in frequency domain, that is amplitude spectrum of h of f, this shows us this is the high pass filter. So how we are analyzing this is the which type of filter? With the help of amplitude spectrum. So amplitude spectrum we are getting when we are converted this h of f into frequency domain. So this is the amplitude. So that's why amplitude spectrum and phase spectrum are very important to analyze the LTI system. Okay, we will see one more numeric. X of t is given here, 2 sinc 40t is applied to a LTI system with the transfer function h of f. The output is given here. Okay, now y of t is equal to 20 sinc 40t minus 200. Find h of f and sketch its magnitude plot and phase plot. Okay, so now dear students, here what is given, input x of t is given, output y of t is given, both are in time domain, and we have to find out the transfer function, that is h of f in frequency domain. So already we seen that h of f is nothing but, that is the transfer function of the system in frequency domain, is equal to output upon input, that is y of f into x of f in frequency domain. So now what is required here? First of all, convert given y of t and x of t in which domain? Frequency domain. So y of t is equal to 20 sinc 40t minus 200. Now to find out the Fourier transform of this, as I told you previously, first identify what is your original signal here, sinc, and we know sinc Fourier transform is the rectangular pulse. One more important thing here, now we need to apply the Fourier transform property, because it is not given only the t, it is t minus 200, means time shifting property here, t minus t0, t0 is the 200. So already we discussed the time shifting property. So see here, the sinc rectangular function Fourier transform we can write in this way. Sinc Fourier transform is rect, as it's a 20 taken outside common. So here 5 is nothing but your t0. So e raised to minus j omega t0. So this is the output response, that is the y of f in frequency domain. In similar way, we have to convert given x of t into frequency domain, that is the sinc Fourier transform is the rectangular. Okay, now what we have to find out? We have to find out the h of f, which is output upon input. Okay, so rect gets cancelled. What we remain? 10 into e raised to minus j 5 omega. Okay, so this is the frequency spectrum, amplitude spectrum and phase spectrum of the given signal. Okay, so in this topic we seen how we can analyze the LTI system, how here we can find out the output response with the help of convolution property in the frequency domain, how we can find out the transfer function, and we can plot the amplitude spectrum and the phase spectrum to analyze the system. Okay, this topic already we covered, that limitation of the Fourier transform and need of the Laplace transform and Z transform. Now already we seen the dielectric conditions of the Fourier transform. We can take the integration, those signals are absolutely integrable. So to show here, one example is given here, that now here suppose your x of t time domain signal is e raised to minus at u of t. So here e raised to plus a of t. So plus a of t means it's a growing exponential, and if for this growing exponential, if we try to convert now this signal into frequency domain, what becomes 0 to infinity e raised to at. Why 0 to infinity? Because of u of t, which is a single-sided exponential, but it is a growing. Okay, if we try to solve this integration, what we are getting output? Infinity. So as it's not perfectly integrable, or our integration output is not infinite, so we can't use Fourier transform, and here for such a type of signal we have to use the Laplace transform. Okay, so thank you for this video.